Another handy tool is the product rule, which is used to find the derivative of the product of two functions. For example, the area of any board is the product of its length times its width. If the length is shortened, the change in area is the width times the change in length. If the width is reduced, the change in area is the length times the change in width. The total change in area is the sum of these. That's true of the carpenter's product, and it's just as true in the language of differential calculus.
The derivative of the product y times z is y times the derivative of z plus z times the derivative of y. Using this rule, it's possible to find the derivative of x squared. Or of x to the third power, or of any power of x. The derivative of x to the power n is n times x to the power n minus 1.
Often, one operation is dependent on another. For example, suppose a vehicle has a fuel efficiency of 17 miles per gallon. That, too, is a derivative. If y is the distance traveled and x the amount of fuel consumed, then 17 miles per gallon equals dy over dx. Say it uses 2 gallons every hour. 2 gallons per hour equals dx over dt. A vehicle's speed in miles per hour is equal to the miles per gallon it gets times the gallons per hour it uses. This is the chain rule. It's used when y depends on x and x depends on t. The sum rule. The product rule. And the chain rule. These three rules represent the grammar of differential calculus. And the value of differential calculus can be seen in the variety of its applications. For example, when a rocket moves with displacement s at time t, the derivative of the displacement is the velocity. Positive for upward motion and negative for downward motion. The derivative of the velocity is the acceleration, which is the same as taking the derivative of a derivative. That is, the second derivative of S. The acceleration is caused by the firing of the rocket. The rules of differential calculus and their applications to physics. Each stands as a solo instrument at play in the art and science of mathematics. Working together, harmonizing, they can blend individual notes or numbers into an exquisite melody.
I just got a letter from a musician named Albert Einstein. He sent it in 1912. The mail was a little slow sometimes. But that's not the reason that I just got it. The reason is because he didn't send it to me. He sent it to a friend of his named Arnold Sommerfeld. And I just got it at the library. Anyway, I wanted to read to you a little bit of what he wrote. He said, "I occupy myself exclusively with the problem of gravitation, and now believe I will overcome all difficulties. But this one thing is certain. I have become imbued with a great respect for mathematics, the subtle parts of which, in my ignorance, I had until now regarded as pure luxury." Einstein worked on gravitation for 4 more years, and what came out is called the general theory of relativity. It is the most fiercely difficult mathematical theory in all of physics. So what did Einstein mean by saying that the subtle parts of mathematics had seemed a luxury? Did he really believe that he was going to get along without doing any calculations? Well, of course not. The point is that physicists have a certain arrogance about mathematics. For example, in today's lecture, you must have gotten the impression that all you have to do is follow some simple rules and you can take the derivative of any function in the world. Well, that's not quite true. Suppose you had a function which looked like an Egyptian pyramid. Well, it's easy to see what the slope is here, and it's easy to see what the slope is here, but right here at the peak, you would be in trouble, because it has no slope at that point. The function has no derivative at that point. Now, I never told you anything that would lead you to believe that that could ever happen. You see, for physicists, mathematics is just a tool. It's to be used in order to accomplish something else. But a real mathematician is the guardian of precision and clarity of thought. What interests the mathematician is the mathematics itself. When a mathematician makes a statement about derivatives, the statement takes into account every exception, no matter how bizarre or unusual, like the peak of the pyramid. That's the kind of subtlety that Einstein was worried about. I'll see you next time.